Okay, guys, we want to start on section 10.5, which is all about tangents. Only a couple of really major rules in this section, so this won't be a very long lesson. As we start the lesson in 10.5, I want to remind you of a couple of vocabulary terms that, as I said in class, are not going to be huge for us, but they may creep up on you on the SAT or ACT, so I want you to be able to understand what the directions in a problem might state, especially if you have no diagram and you have to come up with your diagram yourself. So if you would look at these two tangent lines, both tangents, or both lines, I should say, are tangent to both circles. Here we have a point of tangency, here's a point of tangency. Up here's a point of tangency, and down here's a point of tangency. So both of those lines are tangent to both circles. Those lines are called common external tangents. Okay? Then as you look at the interior lines, the ones that cross in the middle there, that come in between the two circles, again, they are tangent to both circles, a tangent point and a tangent point. These are called common internal tangents. And again, this isn't a big deal. It used to be a big deal in the old book, something that they spent a lot of time on, but this is not a big deal for us. I just want to mention it in passing so that it makes sense to you, so that, like I said, if you see this on a test, a standardized test, and they don't have the drawing for you, you would know how to reconstruct the drawing so that your internal tangents are crossing between the two circles, your external tangents are both staying in the exterior parts of the circles. So just a mention there. Not a test question, not anything that we're going to use in class, but it may be something that you have to use down the road. All right, the first rule today we mentioned early in the chapter, and I want to re-emphasize it as well. Theorem 10.10 tells us that in a plane, a line, and in this case our line is L, a line L is tangent to a circle, that's circle S, if and only if, now remember the abbreviation there, if and only if, IFF, it's perpendicular to the radius and drawn to the point of tangency, that's point T. Okay? So L is tangent to circle S if and only if it's perpendicular to a radius that's drawn to the point of tangency. So I have radius ST drawn to the point of tangency if that particular drawing yields or comes up with a 90-degree angle there, then I know that L is a tangent for sure. And since I have an if and only if statement, that means I have a biconditional. So I can say the line is tangent, therefore I've got a 90-degree angle, or I can say if there's a 90-degree angle, then my line is tangent. If and only if is a biconditional. Now, what have we, how can we come up with a 90-degree angle? What do we know that we can verify or validate that we have a 90-degree angle? Well, one thing is we know that two lines are perpendicular. That's one thing we can come up with. So that's possible, but we also know that if we put an extension in here, if we put an extension from S out to a point somewhere on L, then we know that we can create a right triangle. Now, what I'm saying is, what I'm calling your attention is a circle like that in example 2, where it says identify a tangent. J to L is a radius, and line KL, or segment rather, KL, excuse me, we're trying to determine if that little guy is, in fact, tangent. If KL is tangent, then then for sure we would have a right angle there. Now, how can I come up with a right angle? Well, I can decide if I have a right triangle or not. What information do I have or have I studied previously that can allow me to determine if I have a right triangle or not? Well, we had the rule. If we compare the hypotenuse squared to the sum of the square of the two sides, if I have a less than, I have an acute angle. If I have a greater than, I have an obtuse triangle. And if I have an equal to, I have a right triangle. So it's this concept right here that's going to be significant for me. Remember that C here must be the hypotenuse. And the hypotenuse must be the side across from the right angle. Okay? So as I look at KJ, KJ will be the hypotenuse of this triangle if I do in fact have a right triangle. So KJ squared, well, as I look at KJ, I know that the exterior part is 9, but notice that the interior part is also a radius of the circle. So if one radius is 8, all radii will be 8. Therefore, my prospective or potential hypotenuse would be 17. Okay? So what I would do then is I'm going to check to see if I can find a true statement. Is it in fact true that 17 squared equals 8 squared plus 15 squared? If this is true, then I in fact have a right triangle. If I have a right triangle, I have a right angle at L. And if I have a right angle, then according to Theorem 1010, I have a radius to a point of tangency, which would then suggest, or not only suggest, but confirm, that KL is indeed a tangent. Okay? So as we do the arithmetic here, and they did the arithmetic as well over here, 289 equals 64 plus 225. 289 equals 289. That work confirms for a fact that KL is indeed a tangent to the circle. Now remember, we looked at number 2 as well in class, and we noted that we could use the fact that this potential radius is 18, but we also said if the legs of this right triangle are 6 and 8, then if we know our Pythagorean triples, HF would have to be 10. Well, if part of the potential hypotenuse is already 12, and the total would have to be 10 to have a right triangle, then for a fact we do not have a tangent line. Let me warn you again, if you find yourself saying it looks that way, red alert, okay? Be on your guard. We're not going by the way something looks. We're going by the mathematical evidence that we can come up with that allows us to conclude beyond a shadow of a doubt something is true or it is not true. As we looked in class, let's also look at example 3 here. And as I mentioned in class, I want to caution you again to make sure when you are looking at a triangle like that in example 3, the hypotenuse here that we are wanting to test out is not 8 times x. That's not how we find a total. We add the two lengths together, segment addition, to find out an entire length. So my entire length of my hypotenuse is 8 plus x, or x plus 8, since addition is commutative. So I'm checking to see if the x plus 8 segment across from the potential right angle is equal to the sum. Well, actually, I'm not checking on this one. I am trying to find x, so I know that I've got a tangent. Therefore, I'm using my Pythagorean theorem to find my x. I already know or have confirmed for me that I have a tangent. As they did here, remember, okay, red alert, to square a binomial, you must use the full method. This will not change to x squared plus 64, as badly as we want it to happen. We have to, I think most of you can do this in your head by now. We have to FOIL this thing right here to come up with that middle term. Don't forget. Now, in this case, as you can see over here, I hope I can get this to erase without making a mess of this problem. Yay. As you see over here, my x squares will fall out. And that's great because that allowed me to just solve for x. But if the x squares do not fall out, do not cancel out. Okay? We need to get a 0 on one side of the equal. And then we'll have a quadratic equation. And if that quadratic equation will factor, wonderful. If it doesn't factor, we would use the quadratic formula. Negative b plus or minus square root b squared. All honor students should know this by now. Oops, sorry, that shouldn't have put that C there. That's what I get when I'm talking. There. When I'm talking and I'm trying to write at the same time, doesn't it? So negative b plus or minus the square root of b squared minus 4ac all over 2a is the quadratic formula I would use. Remember that if you use the quadratic formula and once you plug everything in, you get whole numbers. If that happens, that means that that particular equation would have factored. Okay, just a little aside. Doesn't mean that you have to go back and redo anything. It just tells you, I could have factored this and maybe saved a little bit of time. Okay. All right, Theorem 1011 is the second theorem for today. And remember, darlings, that in Theorem 1011, this is the ice cream cone theorem or the clown hat theorem that I illustrated on the board. Anytime we have, let's make it bigger. Anytime we have two segments that extend to the same circle. Now see how this is extending to circle D? And this extends to circle C, to a circle D as well at another point. Anytime I have two segments that extend to the same circle from the same exterior point, which in our case is point B, then those two segments from exterior point to point of tangency, that segment is going to be the same length as from exterior point to point of tangency. Those are going to always be the same. So as I set those equal, let's just look at 4b I have below here. Since I know xy and xw are the same length, then I'm just going to plug in the algebraic expressions that represent the lengths of those segments. Once I solve again, let me again very, very sternly warn you, make sure that once you find x, it is the question that was asked. Okay, finding x, we're done. If they had asked then to plug in and find a measure, we would have to be careful and make sure we go ahead and plug in. This is an example that I pulled out of your book because even though this theorem that we just talked about seems so incredibly simple, when we put several segments on the same circle, it seems like until students get a little bit more comfortable with this theorem, they handle this a little incorrectly, I guess is the best way to put it. So as I'm looking at circle J, and if you remember our vocabulary, circle J is inscribed in quadrilateral STUR, or I could say quadrilateral STUR is circumscribed about circle J. I see that I have the exact type of situation that the clown hat or the ice cream cone illustrates. I've got two segments that extend from the same exterior point. So I have T to A and T to B. They extend from T, the same exterior point, to the same circle, and they go to a point of tangency. That means that TA, which has a value of x, and TB would be the same length. So if TA is x, TB is x. Likewise, U is an exterior point. From U to B, that point of tangency, then U to C, we have the extension from an exterior point to the same circle. That means that UC and UB are going to be the same. So far I have 4 x's there. Down below, R is an exterior point, ice cream cone, to point of tangency, DR and CR are going to be the same. And then finishing it up over here, from S, exterior point to point of tangency, exterior point of tangency on the same circle. If SA is 3, SD is 3. So when I add those values up, I get a 12. And the directions say, and I've cut those off, I'm sorry I did that, but the directions tell us that the perimeter of the quadrilateral is 18. That's given to us. So if I add up the sides, I should get 18. Solving for x is 6, or x is 1.5. Don't get upset when you get a fraction. It's perfectly wonderful, perfectly okay to get a fraction. So please don't let that worry you. One last thing we want to talk about. The directions again ask us to find the length of PQ. So PQ is what we're looking for. I guess I should turn off my highlighter, shouldn't I? Okay, PQ is what we're looking for. That's the length we need. And I set this up for you in class because I didn't want you to go home and get all upset when you saw this. But we know that RP is a radius and SQ is a radius, and they're both extending to tangent PQ. PQ is a common tangent. It's tangent to both circles. Well, since I've got a radius here to a tangent and a radius here to a tangent, I know I've got right angles. Now, what we can do here is we can complete a rectangle, and there's a lot of ways to complete that rectangle. So the way I draw it in now may not be exactly the way that it was done in your class, but that's perfectly fine. I'm going to draw an auxiliary segment in here, and I'm going to go from S over here to the radius such that I have made a rectangle. All right? When I make that rectangle, then from P down the side of the rectangle is going to be 4 units long, because these two have to be the same. All right, since I've got a rectangle, this is a right angle, so that's going to make this guy a right angle. So right in here, I have a 90-degree angle. I also know that the length from R to S is 10, because this radius is 6, this radius is 4, so I have a 10 there. Now look at that 10. That 10 is the hypotenuse of a right triangle. I'm going to try to shade in that triangle without taking a whole lot away from it. I think I better get a different color. That little triangle right there. Okay, that is the triangle that I'm going to use the Pythagorean theorem on to help me solve PQ. Now, again, if this side over here was 6 and the piece I put in the rectangle was 4, that means that I've got a 2 right there. And down here I have a 10, and that 10 is the hypotenuse because I've got a right triangle. If I set the Pythagorean theorem up such that my hypotenuse square equals the sum of the square of the two legs. I'm going to call this one y, this little piece y. Then I can solve for y, and once I have y, since opposite legs of a rectangle are congruent, once I have y, I have what PQ is equal to. Okay? Do not run away from the challenge problems. If you guys couldn't handle the challenge problems, you wouldn't be in this honors class. So it's a great thing for you guys to look at it as a puzzle and try to work it out. Okay? All right. Spend some time with it. Good luck on your homework. And we'll see you next time. Bye.